Numbers has been the most important aspect of mathematics, and today we're going to discuss about numbers and the number system. So starting with numbers, we have seen different types of numbers in the past when we have been discussing in various aspects of mathematical contents. So today we'll be discussing on numbers, and coming with the first and foremost type of numbers is the natural numbers. Natural numbers are the numbers which are expressed in the numerator form, but they do not have the denominator. For example, when I take the natural numbers, they are generally denoted with n, and the set notation for that set of natural numbers would be starting with 1, 2, 3, 4 and so on. The natural numbers denoted by n starts with 1, 2, 3, 4 and ends till infinity. Now in this case, we call them as natural numbers because they don't have the denominator, but they have only the numerator. And the definition here is they start with 1 and the next number would be the consecutive 2, 3, 4 and till infinity. And when I come to the next set of numbers, they are the whole numbers. So whole numbers are generally denoted by W and they start with 0 and they end at infinity. So when I understand the difference between natural numbers and whole numbers, I only see that whole numbers is the set of natural numbers with one additional element, 0. So therefore I can mathematically define the whole numbers as all natural numbers including the element 0. This is how I mathematically denote the whole numbers. Now coming to the next set of numbers which are quite famous in integers. Let me start with the heading. Integers. Now integers are denoted by Z or Z, and we define the set of integers as all the elements coming from minus infinity including the negative and the positive coming out till infinity. So these are the set of integers which includes both negative, 0 and positive numbers. So these type of numbers are set of integers. And what do you understand from all these three? I can denote the integers with respect to natural numbers as I see that all these are the negative natural numbers and all these are the positive natural numbers including 0. So I can just define the set of integers as negative natural numbers union the element 0 which is taken as a special case and then the positive natural numbers. So this is the set of integers which we define in number system. Now next comes the set of rational numbers, which is what we're going to discuss in the present session because that is more important as compared to all this set of numbers. So rational numbers. Now rational numbers are denoted with capital Q. Now we define rational numbers in the set builder form as all the numbers which can be denoted in the form P by Q such that the conditions here are that P and Q must be integers, which we have already discussed in the previous session, and that Q should be not equal to 0. So under these two conditions, we define the set of rational numbers in the form P by Q as rational numbers. Let's see some examples in set of rational numbers. For example, if I take 5 by 2, now I want to know whether this is a rational number. So let's see if it satisfies these two conditions. Then we will justify on whether this belongs to Q. When I say 5 by 2, my P here is 5 and my Q here is 2. So using P as 5 and Q as 2, I identify that 5 and 2 are integers. And I also identify that the q which is equal to 2 can never be non-zero. So clearly q equal to 2 is not equal to 0. Therefore, I identify that phi by 2, according to the definition of rational numbers, is a rational number which belongs to q. So therefore phi by 2 belongs to q. Let me take one more example and see if that belongs to a rational number. Minus 3 over 4. Let's see. So I take again this number compared with p by q form. So I get p as minus 3 and my q is 4, where minus 3 and 4 belong to z, because even negative numbers come under integers, and then q which is equal to 4 is not equal to 0. So these are the two conditions which satisfy q. Therefore I can say that minus 3 by 4 belongs to q. Yes. Now let me go to the third example on finding whether that particular example would be a rational number or not a rational number. So for example, I take square root of 2. So let me just take square root of 2. So in this case, I identify that the square root of 2 can be written as square root of 2 by 1, where this is written in the form p by q. So what would be my p? My p will be root 2 and my q will be 1. Therefore I get, therefore q equal to 1 belongs to z, but p equal to root 2, the square root of 2 cannot be an integer. Therefore it doesn't satisfy the first property, and hence I can say that root 2 does not belong to set of rational numbers. So this is how I understand the rational numbers through various examples. Yes, so we have been seeing different examples of rational numbers. So coming to the continued example, is phi by 0 a rational number? This is very important in understanding rational numbers. So I've taken this as a special example to understand what exactly is q. So when I take the phi by 0, I understand that p is phi and q is 0, where I take phi and 0 belong to z, but it doesn't satisfy the second condition, which is nothing but q is 0, but it should not be 0. Our condition for second case says that q should not be non-zero. Therefore phi by 0 cannot be a rational number. So this is one of the important example in understanding set of rational numbers. Yes, now we'll try to compare each one of what we have considered, that is the natural numbers, the integers, the rational numbers and real numbers. Okay. Yeah. So when I just compare, let me take it as a comparison case between the natural numbers, the next is the whole numbers, next is the integers, the next is the rational numbers, and then next is the real numbers. So I understand that all natural numbers are part of whole numbers, subset of whole numbers, and all whole numbers are subset of integers, and all integers are subset of rational numbers, and all rational numbers are subset of real numbers. The only case in real numbers is that all numbers in the form p by q such that q is not equal to 0. This is the definition of real numbers. So this is how I relate between all the sets of numbers in mathematics. Natural numbers always subset of w, subset of z, subset of q, subset of r, where r stands for real numbers. In this session, we are going to discuss exclusively on rational numbers and the various properties involved in the rational numbers. Now, the first properties what I identify is under addition. plus, which is addition. So the first and foremost property under addition is the closure property. So when I have the closure property, we'll see what exactly is it and then continue from the different types of examples. Now closure property is where if I take A and B belonging to Q, the set of rational numbers which you already denoted by Q. So if I have A and B belonging to Q, then we say that implies A plus B also belongs to Q. The sum of two rational numbers is a rational number, which is nothing but the closure property under addition. Next, for example, you can verify this by taking two different rational numbers and verifying whether the addition also is a rational number. So let's cross check with an example. Let me take two rational numbers 5 by 2 and 7 by 3. We all know that these two are rational numbers written in the form P by Q. Now, so let me add them. The addition would give me with an LCM of 6, and then this would be 5 times of 3 plus 7 times of 2, which would be 15 plus 14 by 6. This would be nothing but 29 by 6. Now I understand this to be a rational number. This belongs to Q. Therefore, you take any two rational numbers and add them, you get the rational number, which is closure property. The second property in addition, under addition for rational numbers is the associative property. So under associative property, we take the same case as closure, but I take three elements belonging to Q. So let A, B, C belong to the rational numbers Q. Then the associative property says that A plus B plus C will always be equal to A plus B plus C if the three numbers belong to Q. So this is one of the property in addition, which is called associative property. For example, you can verify this as in the previous case with three different numbers and just substitute on the left side and the right side and make them equal. So let me take 5 by 2, 1 by 3, 1 by 2 belonging to Q. So let me take the left hand side of A plus B plus C. Then this I simplify and let's see what exactly we get. So this would be nothing but the LCM of 5 by 2 plus 1 by 3 would be 15 plus 2, 17 by 6, and this would be 1 by 2. When on simplification it gives 34 plus 6, 40 by 12. So that is a rational number which you can further simplify to give 10 by 3. Let me take the right hand side and see if you get the same value, 10 by 3. So A plus B plus C is the one what I would like to simplify here. So I get 5 by 2 plus the LCM of 1 by 3 and 1 by 2, and simplified under addition would give me 2 plus 3, which is 5 over 6. And then I take the LCM of 5 by 2 and 5 by 6. Then I get 6 5s 30 plus 10 by 12, which is nothing but 40 by 12, which is in turn 10 by 3. Now I see that the left hand side, which I got as 10 by 3, also gives me 10 by 3 on the right hand side, thus proving associative property holds. Associative property holds in this case. And the third property is the existence of identity. So under addition, identity property is very important because it is very different from the other properties what we discuss. The basic definition of identity itself says bringing back the original element. So when I take, for example, A and I add something to get back A. So we all should identify what should be added to A to get back the same element A. That property is called identity. So in addition, we know that the only element which gets back the original element is 0. So when you add 0 to any element, you get back the original element. So 0 has a special property, and in this case 0 is called the identity under addition. So this is very important in understanding the identity property of various numbers. For example, I take any number, any rational number, say I take 7/2, and I wanted to add 0 to this and see if I get back the same element. So I have, and this should also be equal to 0 plus A. So in this case, when I take 7/2 as the rational number, then I clearly understand that 7/2 when added with 0 gives me back 7/2. In other case, even when you take it in the form 0 plus 7/2 also gives me 7/2. Therefore, we say that identity property holds in the set of rational numbers. You take any rational number and add 0 to that, you get back the original rational number, and this property holds for any rational number using 0. And therefore we say that identity property holds in Q, and 0 is the additive identity. So let us make a note of that. 0 is called additive identity. Under addition. Next, the fourth property which I identify in the set of rational numbers is existence of inverse. Now, in case of inverse property, we utilize the identity because there's a general saying that without existence of identity, inverse does not exist. So when it comes to existence of inverse, let me take the basic property this. As in identity case, I have identified that whenever I add something to the element, I should get back the original element. The inverse property says that when I add something to the original element, I must get back 0, which is the additive identity. So what should be added here to get 0 is what defines inverse property under Q. So we clearly understand that in this case, it is minus A which should be added to A to get back 0. So therefore, A plus minus A is nothing but, we can just refer this as A minus A, which is 0. So this is how I get 0. And similar is the case when I take minus A added with A. So this is how existence of inverse is identified. But most important thing which we must note here is that inverse exists only when identity exists. So let's take it as a property. Inverse exists only when identity exists. Without an identity, you cannot define an inverse. Let's see with some example in rational numbers. Let's prove the property in rational numbers. For example, I take 11/3. It is a rational number. Now I wanted to find its inverse under addition. So before that, we know that 0 is the identity which belongs to Q. Is the identity. Now using this identity, I had to find the inverse of 11/3. So therefore what I do is 11/3 plus something should give me 0. So I had to find that something which gives me 0 when 11/3 is added to that unknown. So therefore this is a mathematical equation which can be solved by taking 11 by 3 to the right. So therefore this would give me x equals 0 minus 11 by 3, which is negative 11 over 3. So this is called additive inverse of 11 by 3. So any number, its additive inverse would be negative of that number, because we already identified here that minus a is the additive inverse of a. So 11 by 3, its additive inverse would be minus 11 by 3. So just with a differing of sign, the additive inverse is obtained from the original a belonging to Q. Now continued from the previous example, let's see what will be the additive inverse of a negative number. So let me take minus 4 over 3 belonging to Q, and I would like to find the negative additive inverse of this negative rational number. So in this case, I identify this to be A, and we have seen in the previous case that the additive inverse of A is minus A. So this can be written in the form of negative A as minus of minus 4 by 3, which becomes instead plus 4 by 3. So this will be the additive inverse of A. So this is how I develop the additive inverses of the numbers by just changing the sign. So minus 4 by 3 would be plus 4 by 3, and plus 4 by 3 would be minus 4 by 3. So reverse of the signs would give me the additive inverses of each other. Yes. Now the next and the last property which we identify in set of rational numbers is the commutative property. Now commutative property is also called abelian property, and let's see what exactly it is. Suppose I take two elements A and B belonging to Q, then the commutative property says that the sum of A and B is nothing but the sum of B and A. That doesn't matter whether order is changed in addition, it gives back the same value. That is what is called commutative property. So A plus B will be equal to B plus A. For example, if I add 7 by 2 with 3 by 5, it is nothing but adding 3 by 5 with 7 by 2. That doesn't affect the addition under commutative property. So let's see if that's really true by just verifying with two different values taken out here. So when I take 7 by 2 plus 3 by 5, that would give me the value 5 is 35 plus 6, and this would give me 10 times of 2, 6 plus 35, and this would obviously be same. So when I just simplify this, this would give me 41 over 10, and this would give me 41 over 10. So this is how I verify the commutative property. Now, so we have identified totally 5 properties here. The first one is the closure property, then associative, then existence of identity, existence of inverse, and then we have identified the last property, which is the commutative property. So using these 5 properties, we will try to see if these properties can also be used for natural numbers, integers, or even the real numbers. So let's see how we can work out. Testing the properties. Testing the properties for natural numbers, whole numbers, integers, rational numbers, and real numbers. So we'll see how we can randomly test. Let's not go in brief, but we'll see whether all properties are holding for each of n, w, z, q, and r. So let me start with natural numbers, which are denoted with n. Now in this case, so let me just identify the closure property. So does closure property satisfy in natural numbers? Yes, you take any two natural numbers and add them, you get back the natural number. So closure property holds. It doesn't fail in any case. So all natural numbers satisfy the closure property under addition. Let me now try with whole numbers. Does closure property hold for whole numbers? Yes, you take any two numbers and add them, you get back the whole number. You take any two numbers, say 0 and 5. 0 plus 5 would be 5, which is a whole number. So closure property holds even in whole numbers under addition. Next, integers. Does closure property hold for integers under addition? Yes, you take any two integers and just add them, you get back again a new integer. So therefore closure property holds under addition even for integers. The next is rational numbers, which you've already seen. This is already proved in the previous cases for each of Q. Then the real numbers. Yes, it holds. You take any two real numbers and add, you get back the real number. So closure property holds for each of N, W, Z, Q and R. So that is how we understand the closure property in each of the sets. Now we will see the next property, associative, and the next property, which is identity, inverse and commutative, also for each of the cases. And we'll see if these all five properties which have been satisfying for Q will satisfy for each of these sets. Next, we will see associative property holding for each of them. Now, associative property is nothing but the extension of closure property. So in this case, when I have two elements added, it comes under closure property. When I have three elements indirectly added, it comes under associative property. So associative property being an extension of closure property and satisfying for natural numbers, indirectly satisfies for even the natural numbers under associativity. So associative property holds under addition. Take any three numbers, add them as a plus b plus c and a plus b plus c, then associative property would satisfy both on the left hand side and the right hand side, thus making natural numbers holding the associative property under addition. The same is the case with whole numbers, where the associative property holds without any failure. Even the set of integers also holds for every integer taken into consideration. Even the set of rational numbers, which we already discussed in the previous case, also holds. And all the real numbers also hold the associativity property under addition. So we know that the identity under addition is 0. So that has already been discussed in the previous case. So using the additive identity 0, we will see if the existence of identity holds in natural numbers. Anyone? We can just make out with natural numbers. We can easily identify that 0 does not belong to n. Natural numbers start with 1, 2, 3 and n till infinity. So 0 does not belong to n. Therefore, identity property does not hold in natural numbers. Therefore, n does not hold closure property. This is because 0 does not belong to n. But the same thing, if you take under whole numbers, I identify that the whole numbers start with 0, 1, 2, 3. So 0 being part of whole numbers, identity exists, and therefore identity property holds in. This does not hold, this holds. So W holds closure property under addition. What about integers? Do they form the existence of identity? Yes, because 0 belongs to Z. 0 also belongs to Q. 0 also belongs to R. So these three are identified under existence of identity. So identity holds So in case of natural numbers, the numbers start from 1, 2, 3 till infinity, and I identify that 0 is the additive identity in general case. But since 0 does not belong to natural numbers, n does not hold identity. Now, when I take the whole numbers, 0 is part of the whole numbers, therefore W holds identity, the identity element being 0. Even the case of integers, 0 belongs to integers, therefore identity holds even in set of integers. The same is the case of rational numbers, where 0 belongs to Q. So identity holds even in Q. And when I take the real numbers, yes, 0 belongs to R and identity holds in R. So this is how I understand the identity properties and the various sets holding the identity property. Now coming to the existence of inverse, let's start with natural numbers. We know that for inverse property in general to numbers is a plus minus a equal to 0, where 0 is the additive identity, and including that minus a plus a should also be 0. So when I take a natural number, we will see whether inverse property holds. So clearly when I see this property, I don't find that natural numbers hold inverse property under addition. The reason being that if suppose I take a natural number, say 3, belonging to n, then if a is referred to as 3 here, that implies minus a is minus 3, which does not belong to natural numbers. So every positive number do not have negative numbers instead of natural numbers. Therefore minus 3 does not belong to n under such that inverse property does not hold in natural numbers. So this is the case in natural numbers, and the failure is only because the positive numbers do not have negative numbers in set of natural numbers. The same is the case with whole numbers, because you take any whole number, the first and foremost whole number is 0, you don't have the negative numbers, therefore the whole numbers also does not hold the inverse property. But when I take the integers do satisfy the existence of inverse, because you have in integers both the negative numbers and the positive numbers. Therefore you take any negative number and just find its additive identity, you get a positive number, and any positive number, find its additive identity, you get negative number. So it satisfies for all z. So z is nothing but so this being the set of all integers, therefore for all a belonging to z, there exists minus a belonging to z such that minus a plus a is 0 is a plus of minus a. This is the case which makes the set of integers hold inverse property. So in case of the set of numbers holding inverse property, natural numbers do not hold the inverse property, the whole numbers do not hold the inverse property, integers hold the inverse property, rational numbers hold the inverse property, because every positive rational numbers have equally the negative rational numbers, and real numbers also hold the inverse property. So the same is the case for all properties identified. So this is how I understand the inverse property. Now next, coming to the commutative property. Now take the natural numbers. The natural numbers have the commutative property holding, because you take any two numbers in any order of addition, it holds back the property. Say for example, I have 2 and 3 belonging to n. I don't have any rule that I should be adding them in order. It is irrespective of order that I add two numbers. 2 plus 3 is 3 plus 2, which equally gives me 5. So this holds commutative property under natural numbers. So commutativity holds in natural numbers under addition. The same is the case with whole numbers. It holds the commutative property, and set of integers also holds the commutative property. Rational numbers holds the commutative property. Real numbers also hold the commutative property. So when I identify the different properties, I see that few sets hold certain properties and few sets do not hold the properties, strictly because of the way the sets are defined respectively.